So we are back to technical topics, and we have decided, hot or not, we are going to do data center networking. Right? It's actually hot, but it's still basically okay. And there are many lectures in this series. The first lecture that we will have today is about topology. All right. So what we will talk about is 5 things: how the data centers are physically put together, what the network topologies are, what is TOR versus OR, EOR, TOR versus EOR, whatever. Data center, what are the issues and what are the requirements? 5 parts. Again, Google comes to our help. They have published all their data centers pictures very nicely. They even have a street view of Google data center. You can go and walk in from your computer and take a look at different rooms in their data centers. Not centers, one center. So basically, I took some of the pictures from their thing. So here's how the data center looks like. Interesting thing to see is that there is a lot of wiring. I think you guys can see it better than I can see from here on the screen. These trays are the ones that are carrying all the wiring, all the cabling. And then there are computers below. This might be one of the older designs, because I will show you some newer designs in a minute. But they are big rooms. And bigger than this is the room next door, which is cooling. So all of these computers produce a lot of heat, which has to be taken out. So the thing that you don't see when you go to a data center is this part. These are all pipes which are carrying different kinds of airs and temperatures and things like that, pumping in. It's like any building. If you take a tour of, let's say, a new building that we have, and I just once took a tour of the Brower Hall, which is one of our new buildings. If you go to the basement, they will show you, it looks like this. It looks like this, basically. A lot of cooling, heating, this, that we don't see in the classrooms. I'm sure this building has somewhere heating, cooling. But this is a big part of the expense and big part of the things that people design, but we are not going to do that because we are networking guys, not the heating, cooling guys. Okay, so at most what we can do is we can design protocols that produce less heat, and we will do that towards the end if there is a time. So because the data centers have to be updated so often, because the technology goes bad so fast, what the companies who sell data center equipment have done is they have designed modules that you can buy the whole module. It has everything inside, including the racks, the computers, the heating, the cooling, and everything else. You just put it on the LAN and you have a data center. Of course, you have to get the power supply and you have to get the water supply, other things connected to it. So this is how it looks like. Ice cube. And this is ice cube is actually not as small as it says. It's not like ice cube. It's really big, but that's what it looks like. A small one would need less than 1 megawatt of power. It will have 4 racks. Medium one will have 10 racks and take 1 to 4 megawatt, and the large one will have 20 racks with 4 megawatts, more than 4 megawatts. It has everything that you need. So as a computer scientist, you can just put the order through and you have a data center. You don't have to worry about the rest of this stuff. Of course, you have to connect it. And the way they measure these things, the efficiency is by PUE, power usage efficiency, effectiveness, which in this case is 1.02. That means that if you need 100 watts to run the computer, all you need is 102 watts from the outside, because there is a lot of energy is spent just in the heating and the cooling equipment running those equipment, moving the air, running the fans. All of that is only 2%, right? So this is very good. So PUE is the input power in to the power used, really used for computing, not power used for fans. Understand the difference? Right? And so that is 1.02, and then you can use it anytime. And the good thing is that they come in all sizes and shapes. And here is a bigger one. Yeah.
Question about PUE. I'm curious about why the definition is power in over power is not the other way.
Yeah. Yeah, so it just might be historical. I thought the same way as to why don't we just measure the efficiency, say 98% rather than 1.02. Efficiency everybody knows. And when they said PUE, first I thought it is power efficiency, but efficiency cannot be more than 1, right? So they just came up with effectiveness. Whoever in the in the heating cooling department decided this. So this is not a networking invention. All right. So the thing is, you can get big one, and then inside they look like a data center. Basically, they have racks and cooling and everything else, big ones. And then this is how the new data centers look like. You just put them one next to each other, and you have as much as you need right now. And then next month you can have as much as you need next month, and next month you can have as much as you need month after that. So this makes it very easy to take out things and put new things, and so on and so forth. And every company that makes data center equipment, almost every company, let me put it this way, because every time I use a straight word like that, you will find one company which doesn't do it. So almost every company that makes data center, and I found Cisco does it, IBM does it, SGI does it, Sun, Oracle, they all make these modules. All right. So, and I noticed them. I don't have a picture of here for Google because I already have this other picture, but Google's data center also look like this. So I'm sure they use it quite a bit. But I'm surprised that Google uses quite a bit of this, because I was thinking that Google probably designs its own data centers, but I may be wrong on that. So this is something that is done, right? And by the way, notice that every slide has references at the bottom, and the references have URLs which are clickable. So if you download a PDF of this lecture, which you can go and download from the website, from the course website, you just click on it and it will take you to the page. All right. So anyway, so this is how the data centers are made. Now we talk about cabling. We come to the networking part of it. This is not very good to look at, but some places the cabling does look like this, or looked like this at least before. Right? At least in the top of on the attic of my house, this is how it looks like. Okay? I can't figure out which cable is coming from where and going where. Right? And so what they want to do is more like this, where every cable is numbered and pretty well done. This is called structured wiring, and that is what the norm is today. Everything is very well structured, and you can figure out where it is coming from, where it is going, by looking at the cable and things like that. And the equipment actually looks much neater. So here you can see the rack. In the back of the rack, they have the cables, which might be even color coded and things like that, and they are very neatly arranged. They are very neatly arranged. Some of the cables, after they come out of the rack, they go to the top, and in the top there are 3 layers. You can see 3 layers. The top layer is, the bottom layer is signaling, middle layer is power, and top layer is fiber. So what is signaling? Signaling is Ethernet. Basically your Ethernet signals go through the bottom layer. And then next is power, and the top layer is fiber. And I really don't know why the order is this, but this is how it is right now. I can imagine that the Ethernet, I would have thought that the Ethernet would be far away from power as much as you can, but they are very close to each other, middle and bottom. Yeah.
So if the bottom is Ethernet, what is the top fiber transmitting?
Right. So it is. The thing is, I am not sure this order as to why this order was selected, but it is quite possible that this came later, and they just created a new layer. But don't take my word for it. Okay. and then there is and then there is wiring cabling also in under the floor. Okay, some places they would prefer, you don't need to have both. Some places they would prefer to have under the floor, and most of these floors are false floors, as you can see there, for heating and cooling regions. So these floors, you can see there are holes in the tiles. Those are blowing airs, and and underneath those tiles you might see figure like this, where there are some more cables or some cables. The cable coming to these racks. Okay, and then the data center itself has a certain standard layout. At one place they will have lots of power supplies. This is the place where everything comes in. The next to that is the telecommunication, where the outside lines come in, and then next to that is cooling system, and then there are these hot, cold, and aisles and so on and so forth. Now, why these things are at different places is not actually our business to know. I mean, basically, I really don't care, but I just want to let you know that there is a standard for all this, and this is how they are put together. And the standard is called ANSI TIA 942-2005. All right. So ANSI is American National Standards Institute. TIA is Telecommunication Institute of America. Telecommunication Industry Association. Sorry, it is Telecommunication Industry Association. Telecommunication Industry Association. So TIA. So basically, TIA put together this standard, and then ANSI approved it. So ANSI is American National Standards Institute, which does everything, and TIA is only interested in telecommunications. So that's how it is. 2005 is the year, obviously, and TIA 942 is the standard, and there might be other similar standards that if you go to TIA website, you can find them. But basically, what they do is they want you to, they recommend that you set up your data center like this, where you have the entrance room, where your lots of access providers are the carriers, are the companies like AT&T, Verizon, who provide networking. Their cables come in. Right, and then so that is the entrance room. From there, basically you come into the computer room. And then next to computer room you have these telecom room, and I think the telecom room might be more like voice telecom, but the data is coming through here. And then in the computer room, what you do is you divide into many different areas. So first there is MDA, which is the main distribution area. From there, you go to horizontal distribution areas, HDAs. And from there, you go to equipment distribution areas. So what it is if you go back to the previous picture, the first few things here might be simply patch panels. Actually, they used to be patch panels before, but I'm sure by now they're all automated, so you can change things remotely. But in my days, or in some days ago, basically you went and plugged it in. So that is what distribution area means. Okay. So there is MDA, main distribution area, and then horizontal distribution area, and then the equipment distribution area. Equipment distribution area is basically the racks. Okay, and to get to the rack, you go through the horizontal distribution area. Now there is a GDA. GDA is zone distribution area, which is basically, now I don't know what zone distribution area is, but basically, if you were to divide into different, zone is, so I will have to figure out what zone is, but basically you have to divide an area into different zones, and whatever that zone means, then there is a distribution area there for that. But we see two words here. One is TOR, T-O-R, and then one we see EOR. Right here, EOR. Those I will explain in the next slide. All right. So the summary of this slide is that the distribution is 3 levels: main, horizontal, and equipment. All right, zone. So zone is optional between SDA and EDA. That's all it says. But So we don't know. And then a backbone cabling is the connection between the HDA, MDA, and all those are basically the backbone cabling. So these cables are backbone cables. These cables. All right. So basically, now we come down to how the data center networking is organized. So initially, what happened was that most of the companies, what they did was they had campus switches that connected to the campus distribution area, and then campus core, and the servers were hanging out of that, and then they had the edge routers which went to the telephone company, to the carriers. That slowly became standardized as follows, is that basically they have servers. On the servers they have switches which we call access switches. Alright, servers are connected to access switches. Access switches are connected to aggregation switches. Aggregation switches are connected to core switches. Alright, and so there are now 3 tiers of hierarchy. You go to access, aggregation, and core. And so all the servers are at the bottom, not in the middle anywhere. And then from core you go to the outside. So the important thing to notice is that there are 3 tiers, and their names are access, aggregation, and core. There are 20 to 40 servers per rack. I suppose everybody has seen a rack, at least, right? And so, has everybody seen a rack? Is there somebody who has not seen a rack? If you have not seen it, then basically you want to walk into one of these labs, or you can look through the glass through one of these labs, and you will see a rack in many labs. In fact, our lab, the IT lab on our floor is locked, so you cannot see from outside. But in some labs you can see through the glass. So these are plain, racks. And we showed you the picture before a minute ago. Anyway, so there are 20 to 40 servers per rack. Each server is connected to 2 switches. So that is an interesting thing to notice, that everything is dual connected. You see, this server is connected to both access switches, right? And this switch is connected to 2 switches, and this switch is connected to 2 switches. Everything has a redundant connection. You understand why? Why?
For redundancy?
Yeah, reliability. Right? If something fails, the other one continues. So each 2 access switches. Right now, 1 gigabit is common, but 10 gigabit is coming in. So if you buy a new thing, you buy 10 gigabit. If it is the old thing, 1 gigabit. For example, at your home, my home, in every lab, 1 gigabit is common today. I mean, you don't buy anything less than 1 gigabit, right? But if you're a company, then you spend 10 gigabit. Access switches connected to aggregation switches. Aggregation switches connected to access routers. Now you see the word routers and switches. What is the difference? Yeah.
Routers, it's layer 3, switches over
Layer 2 and layer 3. Yeah, good. So these are layer 2 devices. These are layer 3 devices. These speak Ethernet. These speak IP. Access router connect to the core routers. Actually, this is wrong. So let's see. Aggregation routers connect to the core routers. Access connect to aggregation. What is happening here? Okay. These slides are hot off the press, right? So there are some bugs in there. Basically, if you can correct in your slide, you can see access connect to aggregation. Aggregation connects to the core. And then this one can go away, okay? Basically, that's it. There's nothing else, It's not, there's no cycle backwards and forwards. Access doesn't connect to core. Aggregation connects to the core. Then aggregation layer is the transition point between L2 and L3. All right. And nowadays there is a requirement for low latency, because if you are running a stock market brokerage firm, a few nanoseconds and microseconds can make $1 million difference, right? So you don't want your messages or your sales order to be stuck in an Ethernet queue. Which one?
Access routers connect to core routers. There will be edge routers.
Yeah, right, but access is not connected to anything like that.
I mean, you meant edge routers instead of access routers.
Yeah, the core router is connected to the edge routers. Edge routers are connected to the core routers. Core is connected to aggregation. Aggregation is connected to access, right? Yeah. So the first thing should be edge, maybe. So edge routers connect to the core routers. Here, he says edge.
It's in and out of data center.
Yeah. So edge routers. I think that will fix all the errors. And by the way, all the information has a reference. So I'm kind of putting every reference that that information I have taken from. So here is a paper from SIGCOMM. Actually, SIGCOMM paper became CSEM paper. So this is where it came from. Core routers manage traffic between access routers in and out of the data centers. Okay, I think that I know what is the problem. I know the problem is no. The problem is different people use different terminology. So Greenberg is using terminology here which is not the same as used by the rest of the industry maybe. And so this picture came from Cisco. Okay, and this description came from Microsoft. And I didn't realize that there is some difference in the terminology. All right, I will fix it later on and probably update it. But right now, let's live with whatever we have. Okay?
Routers are also called access routers, right? They're not access switches.
Yeah, right. So there is this terminology thing, which is basically the thing is when you read the book from Cisco, it is very clear about what they are talking about. When you read from Microsoft, they are very clear, but when you read them together, then they are confusing. So that is the thing that I have to basically straighten out. But right now, let's just try to see. We just try to follow the figure as our main guide, because I think that figure is more authoritative, in my view. That Cisco book was basically more authoritative, whereas people writing papers, BL2 is a paper, right? I mean, a SIGCOMM paper. People are not up to date on the industry. So, anyway, all switches below the access routers. Okay, so if you call aggregation routers, what are you saying? Edge routers. All right, everything is basically so. That thing is, there is no new information here. The main thing is that everything is dual connected. Period. And most of the traffic is internal. That is the key point. Is that originally, sorry, am I going backwards or forwards? Backwards. Okay. Originally, when the data centers were designed, or before they were designed, the traffic was going north-south. Right? Now, today, they don't go north-south, they go east-west. Why? Because these servers are talking to each other more than they're talking outside. And that is a key change in the traffic pattern. And so that is the important point to notice. Most traffic is internal to the data center, and the network is the bottleneck. Some of the links have utilization of 80%, and most of the flows are small, and so on and so forth. So basically, the Microsoft guys did some measurements that most of the flows are, mode is 100 megabyte. What is a mode? Anybody knows what is a mode? Anybody knows what is a median? Huh? Yeah, mode is the most common entry. So if you look at the graph, wherever the peak is, that is the mode, right, is 100 megabyte. And DFS is the distributed file system, which is the commonly used file system, uses 100 megabyte chunks, and that is why there is a mode there. Because if in DFS, if you're using DFS and you say, okay, I need this file will be broken into 100 megabyte chunks, and it will be sent one chunk at a time. So your each flow would be 100 megabyte. And then there will be a gap, then there is another flow, and then there is a gap, there is another flow. All right? Makes sense so far? All right. So now, where do you put the switches? The first switches that we call access switches. You can put them on the top of the rack, or you can put them at the end of the rack, end of the row. If you put them on the top of the rack, then you have a shorter cable to the servers. Right? And if you put them at the end of the row, then you have one place where you can change from 1 gigabit to 100 gigabit to 10 gigabit. You can keep changing the networking and don't have to touch any racks. So they both have their advantages and disadvantages. Which one you have to change more often? The cabling or the switches? Right? And so end of the rack puts all the networking equipment in one rack, and top of the rack is, puts shorter cabling. And so we already said all of this is that the difference between these two is easier cabling. The rack is not fully populated. The problem is that if the rack is not fully populated, then you have unused TOR ports. So here's the thing. Suppose you have, this is a 24 port switch and only you have 4 servers, then 20 ports are not being used. In this case, you don't do that. Why? Because you can connect any server to this switch. Right? So you have less networking equipment, less networking investment. Alright, if the rack is not fully populated, there are unused TOR ports, which is basically money gone down the drain. If rack traffic is high, difficult to add more ports. And for some reason, suppose you need more than 24 gigabit, then you cannot put 25th. With the other one you can put. With the end of the rack, you can put one more switch and connect to that one. There is a scalability. Upgrading the speed is same thing. You can easily upgrade the networking equipment with the other one. The main negative of the ER is longer cables. Now you have to manage the cables. Equipment is good, but the cables are long. Servers can be placed in any rack. That's another positive. Server can be placed in any rack. Ports can be easily added, upgraded, and so on and so forth. So that's very good, right? So you have decided, you have to decide which one is cheaper or better for you. Now, the thing is that you just don't need the servers and the switches. You need a lot more. What you need is lots of what we call application delivery controllers or application delivery services. For security, you need VPN servers, you need IDS, intrusion detection systems, you need firewall. For performance, you need load balancers. For networking, you need DNS. What is DNS? Domain name system. DHCP. What is that? Dynamic host control protocol. Somebody is saying very slowly, but other people are not even saying. NTP. Anybody remembers? Nobody remembers NTP. Network time protocol. FTP. File transfer. Everybody knows that one. Radius. Yeah, okay. You got the first 2 words right. No. Remote access. Basically, and I can't remember myself the whole thing, but basically this is the server that you use for your remote authentication. Okay? For remote authentication. So when you sign in, for example, here in WashU, the authentication will be some other place, central place, and that is the Radius server. Database services, SQL. So all of these things which are shared by all the servers, the best place to put them is between access and aggregation. This is the place. Okay? ADCs are application delivery controllers. They are located between the aggregation and the core. ADCs are located between the aggregation and the core routers. They are located between the access and the aggregation router.
Could you say what the ADC is one more time?
Application delivery controller. Okay. Aggregation and the core. Aggregation and the core, there is nothing. Generally it is what?
Between the aggregation and the core.
Yes, the text is correct.
The statement is correct, the figure is not. According
Figure is not. And the figure came from Cisco's book. No, this is then coming. This came from Cisco white paper. Okay, so this. Okay, I will have to fix that. I mean, I will have to, another iteration on this one, which, we'll find on the website again. Either the figure or the text will be changed.
A
But,
lot of the services are not required when you do this traffic. A lot of the services are not required.
right, so it makes sense to put them one layer higher.
One layer higher, because if you need them, just go one layer higher.
Yeah, yeah. I mean, what Subharti is saying, by the way, Subharti, his PhD thesis is on ADC, so he knows more about everything than I know about ADCs. Application delivery. So application delivery, he's saying, is that really this layer is for east-west traffic. So if you want to go from here to there, you would go through this, from this access switch to the aggregation switch and come down. Right? And so it may not require you to go through this one. Now, having said that, what I'm thinking, Subharti, is that might be the past. Today is even the east-west traffic needs firewalls.
So they always needed firewalls. They
Yeah.
have always
Even east-west traffic.
Yeah. But the point is that it is not always like 100% of time does not need firewalls. So they always go to the aggregation layer,
Yeah.
put the firewall up.
Yeah.
The only part of the traffic that requires a firewall to go up.
Yeah.
Other traffic can just pass.
Yeah, so that makes sense. And second reason it makes sense is because you really don't want to put any of this in the layer 2. All of this belongs in layer 3. So, I mean, why are we putting it here? So this picture is wrong, clearly wrong. Picture is wrong, but the text is correct. If you go between the aggregation and the core, that is where we would have put these services. Now, we had some discussion. I mean, I don't know. I just want to make sure everybody understood what I said. If you didn't understand, let's go one more time. Firewall, etc., are layer 3 and higher services. They are not Ethernet services. Right? Ethernet devices cannot look at IP packets or IP headers, things like that. So we need to really put it where the layer 3 is, and layer 3 is really here in the core, between the core and the aggregation. So all these services belong there, not here. Already got it? All right. Oh, there is one more sentence here. Stateful devices on the aggregation layer. And so what is stateful? Stateful means state of the TCP connection. Now, this is a little bit complicated. Let me explain. Is that many devices are stateful, many devices are stateless. For example, when you do DNS, you ask for the name, and then if you go back to ask the name again, it doesn't remember that you asked for the name already. DNS is totally stateless. In fact, routers are totally stateless. If you send a packet to Germany, it will look up in the routing table and send it to Germany, and then you send the next packet to Germany, it will look up the router again, and the router will look up it doesn't remember that the previous packet I just sent was to Germany. All right? So they are all stateless. After one packet is gone, they don't remember what they did. Second packet, they have to start from the beginning. Those are totally stateless. But firewall remembers that you set up a connection, that the connection is not still acknowledged, that you asked for this object, and now you're going to ask for this object, and things like that. That is totally stateful. It remembers what you have done so far and what you should be doing next and not what you should not be doing next. It knows everything. All right? So those are stateful services. Stateful services such as firewalls have to go on the aggregation layer, which is actually, I think, we kind of agreed that most of these things have to go here, above the aggregation layer and not below. Now there is one more detail as to how do you connect these switches. So you see, the normal method that we have is that you connect the top of the rack or the end of the rack, doesn't matter where they are, a server to two switches, and two switches to two switches, and two switches then going on to the higher layers, right? So the aggregation switches actually have two layers, layer 2 and layer 3. Everything that has layer 3 has layer 2, by the way, right? So these are the layer 3 devices, these are layer 2 devices, but you can connect at the layer 2 or you can connect at layer 3. So this would be an IP link, this would be an Ethernet link. And so if you connect, this is a common method, let's say connect, which is called looped triangle. So there is a triangle here, and there is a triangle here, and then there is this loop. So this is a looped triangle. If you connect like this, what is going to happen is that a spanning tree is going to be run between these switches, Ethernet switches. And the spanning tree will say there is a loop here, and you don't want to have a loop, because if there is a loop, then the traffic will just circulate. So it will say, please disable these two links. So these two links are there, but they are blocked by the spanning tree. And so the real topology is you can go from here to there, but not there. This is blocked. From here you can go there, but not here. You can go from here to there, but not here, right? So this switch is actually not being used at all. So only this switch is working from both the switches. Both the switches are going to go to the same switch. All right. So now you are not really using 50% of your equipment. I mean, not 50%. At least you are not using one of the two switches here, and you are using these two switches, but you are not using this switch. Right? So that is the problem. So you don't like that. Well, I paid for a 10 gigabit port and it cost me $1,000, but I'm not using it. Spanning tree simply says don't use it. So the next option is to connect like this, looped square. Now these four switches will run a spanning tree, and the spanning tree will say that please block this link because there is a loop. Now once you block that, then there is no loop. Okay, and the problem with this is that oversubscription doubles if failure. Now what is oversubscription? Oversubscription is that you have more traffic coming in than going out. Actually, oversubscription comes from the airline industry, where they book more seats than they have seats on the plane. You know that? Right? Every airline books more seats than they have seats on the plane. That's why when you go to the airport, they say, well, we are overbooked. If anybody wants to, do this, we'll give you so much money. So what do you do on the Ethernet? We do the same thing on the Ethernet. We put maybe 40 1 gigabit links coming in, and then we generally have only one 10 gigabit link going out. How much oversubscription we have? 4 times. We have 40 gigabit coming in and 10 gigabit going out. So the oversubscription is 4 to 1. We hope that not all 40 will be sending 1 gigabit at the same time. So that is called oversubscription. Now, so all the links are oversubscribed. And therefore, if right now you are using this way and this way, 1 gigabit here and 1 gigabit here, right? Because you are using both the ports. You can send 2 gigabit. But if this link breaks, then both 2 gigabit will go here. Now you are oversubscribed by a factor of 2. Understand? All right. So that is negative of that one. Positive is that you are using both the links. Then you go to the third one, which is loop free U. Loop free U, and here the link is at the third layer. There is no link at the layer 2. So Ethernet, when they run these switches, when they run spanning tree does not find a loop. Doesn't block anything. All right, and so the problem is there is no L2 communication between the aggregation switches. If any link fails, if any of these links fail, this switch cannot talk to this switch at layer 2. It can talk at layer 3, but not at layer 2. It cannot tell the neighbor, look, my link is broken, let's reconnect or do something. Right? So your layer 2 communication is broken whenever any link breaks. The last one is loop-free inverted U. And so this one basically has a link at the layer 2, and these 4 switches, when they run the spanning tree, then nothing is blocked, so that's good. But the problem with this one is that black holes on some failures. If something failed, then the traffic just goes into the dustbin. Okay, so let's see what will happen. Let's say this thing failed here, or this link failed, and the traffic goes to this switch and it cannot get out anywhere. Alright, so anyway, there are 4 possibilities, and you can see that each one has a negative and a positive. By the way, all of this information came from this book. So somewhere earlier I have given the complete reference to the book. You can read that book. The book is very good. This is one of the recommended books that I put among the 3 books. I think it is one of the Safari books, so you can get it online. The main thing about Safari is that only 8 licenses are there with WashU. So if 8 students are reading, the 9th one cannot read it at the same time. So don't read it on Sunday night when the homework is due on Monday morning. Okay? Because everybody will be reading at the same time. So basically, read it earlier. All right. Yeah, go ahead.
Question about the loop square.
Yeah.
Is that the gap between 2 switches, is that because of the spanning tree protocol?
Which figure are you in? The loop?
The loop square connection.
Loop square. The black?
Yeah. Is that due to the spanning tree protocol?
Yeah. See, whenever a spanning tree discovers a loop here or over there, triangle or square, it breaks a link.
So the loop square has can we say that it has an advantage over the loop-free inverted U in the sense that if the link
there is no black hole. Clear advantage. So what I have done is I have tried to put the clear disadvantage on everything, right? So there is a clear disadvantage of this is black hole. Yeah.
For your loop triangle, would it be fair to say that the disadvantage that it has is only based on the protocol? If you don't use spanning tree, then you have...
Good. That's a good observation. That's a very good observation. So when we talk about a spanning tree, which we will at some point, then we'll see why we need to get rid of a spanning tree, just like this reason. All right. So data center networking issues. The first is that oversubscription is an issue. We have in the same rack there is no oversubscription generally because you just get 1 gigabit and 1 gigabit out to the switch. But from the switch onwards, you have 1 to 2 to 1 to 20 oversubscription. For example, you might have 32 times 10 gigabit down, but only 8 times 10 gigabit up, which is 80 to 320, 4 to 1 oversubscription. Core routers are oversubscribed 1 to 240. 240 times more traffic can come in than it can get out. Right? So generally basically your idea is that you want to really keep people who are talking too much together. Because if they have to talk over the backbone, then backbone is already oversubscribed. It will be a big problem, right? So you want to put services which talk to each other in the same rack. Either that or you change your network. So a lot of people are doing research on how to change the network so that anybody can talk to anybody. Right? So moving across subnets is painful. But that's another problem, is that Ethernet is good, IP is bad. And you will hear this lecture all the way through this IEEE and throughout the data center thing, because Ethernet made few decisions early in the game which really are helping now 40 years later. IP made some decision early in the game which are hurting us 40 years later. And one of the decisions is how to address things. Ethernet addresses by the name, IP addresses by the location. So your IP address is row 3, row 2, chair 4. If you move to that one, your IP address changes. Big problem. Your Ethernet address is fixed. Whatever your name is, that is your Ethernet address. You move there, you're still the same address. You move there, it is still the same address. I can still send a packet address to you, you will get it. So the Ethernet does not care for the location. It just gets the packets to the right place. And that's big advantage when you want to move the virtual machines around. You can move any service to any other place. But if you don't go to layer 3, we are all happy because it will get there. If I have to go through layer 3, then I have to find your location. So moving across subnets is painful, requires reconfigured IP addresses and VLAN trunks and so on and so forth. What is VLAN? Virtual LAN, and I have a whole lecture on that one right now. I don't know whether we taught you in 473 or not, but since this class is on virtualization a lot, I thought I will put at least few slides. So I have VLAN. So anyways, this is very difficult. So basically, some services trample on each other. Overuse by one service affects others. The second thing is because of the oversubscription, everybody affects everybody else. If you are oversubscribed, there is only 1 gigabit and 240 people are trying to get in. What is going to happen? Somebody is going to be killed, right? It better be not you. And so that's another problem. Poor reliability. One access switch failure doubles the load on the others. And so now we want to design network topology that will not have these problems. Other issues are underutilization. That we are not using all the paths. Everybody is taking the shortest path, and that's a problem. You were told in 473 the shortest path is best, right? But if everybody took the shortest path, what will happen? It will be congested and everything else is free, empty. Right? So we want to do something different, right? So multiple paths exist, only one is used. Even if there are multiple shortest paths, we don't use parallel paths, we just use one.
And shortest path is also good only when latency. Shortest path is good only when latency is an issue, right?
Well, when the latency is issue, but then you have to worry about the congestion, because latency is the one that affects the congestion. And if it is unloaded, if it is underloaded, then yes, shortest path is good for latency.
All paths are almost equal always.
Okay, no, hold on. That thought, keep up with that thought, because that is not true. But what we do is, if there are two paths which are equal, then we do ECMP, equal cost multipath. So that is what is common nowadays, both at layer 3 as well as layer 2. Ethernet as well as IP, both will use ECMP, which is equal cost multipath, which means that if there are two shortest paths, half of the people will take this, half of the people will take that. I'm sorry, what did you say? You said that.
Yeah, in a data center, the latencies are very small. There are more chances of all paths being equivalent to each other, rather than the shortest path being better than any other path. So
shortest path being okay, hold on. The first statement you made is that all paths are equal. That is not true. If you are going from this rack to this rack, that is short path. If you are going from this rack to that rack, this is a long path.
The difference in latency is not as much as in a
Okay, hold on. So we are talking about the latency, about the levels of the packet sizes here. The latency here is 3 packet sizes, because the queue is 3 packet sizes. You are going through only one switch. Over there, going through 2 switches. So So I think the difference matters. So basically, the idea is that ECMP is used. I think I will stop right there. Let's see what is next. All right, I will just stop right there.